Throughout history, water undoubtedly has been the most important resource for successful civilizations as well as thriving animal ecosystems. This is perhaps best given or exemplified by the Roman aqueducts as shown below. It was very important or evident to our early brothers and sisters that having sustained and easy access to water was paramount for the successful survival of their civilization. As we move throughout time, this has not changed. We are still extremely dependent on water in more ways than we can even imagine. For instance, the agricultural industry in the United States consumes 137 billion gallons of water per day, while the power industry consumes 190 billion gallons of water per day. These two sectors account for more water usage than any other industries combined domestically. And unsurprisingly, this has led to areas across the United States that look like this: semi-arid, dry regions that are water stressed and facing extreme water scarcity. And as we continue to have anticipated population growth by 2050, with some estimates anticipating 41% population growth, and some estimates indicating that because of this, energy demand and food demand will increase, and thereby water demand will increase to the tune of 234%. Where is this water going to come from? And it's easily enough for us to say that water is the giver of life and master and servant of mankind, and we should start thinking about these problems sooner rather than later. And this leads us to our market problem. How can we meet this projected 234% increase in demand, especially when only 3% of all the water in the world is fresh water, and of that 3%, only 30% is usable ground or surface water? Finding low cost and new ways to treat non-traditional water sources is going to be paramount. And when I'm talking about non-traditional water sources, I'm talking about water sources that you wouldn't normally think of when you think of where to get water from. So for example, I'm talking about produced waters. And produced waters are essentially waters that are produced from some sort of industrial activity. And for this instance, I'm going to be talking about produced waters from oil and gas companies. And it's quite astounding. When you actually drill for oil, you don't just get oil that comes up. You actually get water and oil, and actually a lot more water than oil. In fact, you get 10 barrels of water for every barrel of oil. This is actually astounding and kind of mind-boggling, really. And it's estimated that in the United States alone, we produce 630 to 840 billion gallons each year. That's 1.72 to 2.3 billion with a B per day. The average urban area consumes about 300 million per day, to put that in perspective. And so currently, a lot of this is actually just re-injected into the ground, 90% of it back into the ground. 10% of all the produced water is actually low enough in salinity that it can be sold and then blended with fresh water. So the way this works really is because you're drilling at different sites, you get different salinity waters when you bring up the oil. And some of it's low salinity enough that they don't have to treat it enough, and they can just mix it with fresh water and sell it. And they do right now in Bakersfield, California, and selling it around $1.25 to $1 per meter cubed. And so further though, this water has to be re-injected because it's just too saline to be treated any other way, especially with conventional methods such as reverse osmosis. It has too much stuff in it for RO. So they have to inject it in the ground. And I put these asterisks because it's actually a liability. These things they're finding out are causing earthquakes, and companies are facing litigation. There's a whole host of environmental concerns, and it's turning into an issue, and they need to figure out a way to deal with it. And so our value proposition is to turn this liability into a valuable commodity for these companies. Competing technologies do exist. They're either thermal or membrane based generally, but none of them really work that well. But let's go ahead and talk about thermal desalination first. And it's what you would think. It's actually just heating up water and then cooling that vapor and then condensing it as fresh water. And this is usually mechanical vapor compression, membrane distillation, or just traditional distillation. The problem is it's very energy intensive. As I mentioned, about 2,400 joules per gram is the enthalpy of vaporization for water. So we have to avoid this first order phase transition in order to get by this, because we definitely don't want to do things that employ these very high energy intensive phase transitions. The other thing is membrane desalination, but again, this comes with its own problems, as I was alluding to with RO earlier. Essentially, the pressures for these produced waters are just too high for these membranes to handle. If they even did work, you would have such high maintenance costs for membrane replacement. So this also is not an option. One membrane technology that I have not talked about is something called forward osmosis. And this is quite attractive because really in the forward osmosis, you're actually using something called a draw solution, which is placed on one side, and then you have a feed solution. And the feed solution has a lower osmotic pressure than this draw solution. So essentially, you're still relying on a membrane that's in the middle but you're separating these two different solutions. And because of this difference in pressure, you get an equilibrium, and water passes through the membrane. Same principle as RO, except you're not forcing pressure using natural osmotic equilibrium. So this is essentially an energy-free process. The draw solution gets diluted, then you have to recover the draw solution and you get your product water. This is where the problem comes in, because it kind of has made FO kind of a niche technology, because this draw regeneration is typically very, very expensive. And what we've done is we've tried to curb down the cost of this regeneration and tried to do it with an energy source that is essentially free, and that's solar energy. And so what we've come up with is a way to take this wastewater, do something called engineered FO, where we use a special draw solution that's thermally responsive, and it responds to these small temperature changes from the sun, and we can induce these phase changes as seen here, where you get clean water on the top and then your draw solution on the bottom, and then you get your treated water and you can recycle the draw solution. And so we actually did this, and it worked for current oil and gas waters here in California. So we went down to a couple fields that are operated by the CRC in Kern County, South Mountain, and Elk Hills. We did a couple others also, but they have TDS levels, for example, these two, 53,000 and 30,000. And just for normal seawater RO plant, it's about 30 to 35,000. So this is South Mountain especially is much higher. Higher suspended solids, 29 ppm. They have VOCs, volatile organic compounds, yes. They have metals, yes, and they have organic salts, yes. So it has everything in it. It's nasty stuff. And what we've shown is that we can take this, we can do this gravity filtration, our osmotic step, where we dilute our draw solution, and we put it into something called a photonic heater, which essentially converts solar radiation into heat. And then we do a nanofiltration polishing step that removes a residual 1% or 2% of the ionic liquid that maintains itself in the aqueous layer after it phase separates. And as you can see, we can go from something that looks like this to something that looks like this and show about 99.97% pure water, which is a great accomplishment in itself. And so really the business model is, or how we're thinking about this, is contract-based, because they already have the capabilities to handle these massive quantities of water and then sell it to a current market that exists to agricultural communities within Bakersfield or other communities that are nearby oil and gas producing regions. How financially stable is this? We did a brief techno-economic analysis that we can talk more about later, but it was 5,000 liters per day, considering CapEx, OpEx, and varying discount rates. And of all our models, about half show that we can do this under $1 per meter cubed at about 3 kilowatt hours per meter cube of energy intensity. And this is all using experimental lab-based data, and also at a small scale. If we increase the scale and get better data, better experimental values from actual pilot plant studies, this should even further reduce the cost. The team of how we're doing this is essentially Lawrence Berkeley National Lab and then the California Resources Corporation in Bakersfield, California. And the members, part of this team are myself, Dr. Andrew Haddad, I'm a research scientist at LBNL. Akanksha Menon is a postdoctoral fellow at LBNL. Robert Kosecki is a division director at LBL, and Ravi Prasher is an associate lab director at Lawrence Berkeley National Lab. Within this ecosystem, we're planning on going down to these oil fields once COVID gives us a break, and to deploy our 5,000 liter per day prototype, and to see if we really can achieve $1 per meter cubed of water produced. Then this water will eventually be sold to the agricultural community that surrounds these oil fields in Bakersfield. And as I said, currently they already have this in place where they're selling them 10% or approximately of their current produced water. If they can increase this value to even higher percentages, this is going to be something that's going to be very attractive for the oil and gas companies, but as well as for us to expand our horizons. Thank you so much for your time. My name is Andrew Haddad, as I said, and I appreciate your time and effort from taking out of your day to listen to this. And I'll see you guys on the 2nd. Thank you. Bye.